Okay, the last chapter we're going to look at out of this book is called nonparametrics. Nonparametrics is a set of statistics designed for some specific purposes. It's designed for really small samples, meaning that you have less than 20 in your sample, and that's pretty common among the groups that are participating in these classes. It's common for outliers, those at either end of a spectrum, or for strong non-normality. Those of you who are in counseling or special ed, when you have very small, specific kinds of people participating in your study, not that they're not normal, they just don't fall in with that normal range and that bell curve. There's something different about them. This type of test is appropriate for that. And the other one, and I'll bring this up again later on, is things where you're using rank order data. And there's some debate about this, but we'll get into that in just a few minutes. First one to look at is something called a Mann-Whitney U-test. It's a non-parametric test designed for data from independent sample design, meaning that you have two groups that you are comparing, and you want to know if they differ in their ranking or their rank order based upon the group that they're in. This is kind of like an independent sample t-test. It's just designed for non-parametric use. So, for example, suppose we thought that early training for tennis players might have an impact on their ranking, meaning that somebody thought that those who had training very early on would be ranked higher in the tennis world than those who did not. So we could rank the data something like this. And these letters over here are the initials of the players. Here's their national ranking, 1, 2, 3, 4, 5, and here's the answer to the question: did you receive intensive early training? So you can see those who were in group rank 1 through 3 said no. The one that ranked number 4 said yes, etc., etc. We want to know, does this intensive early training impact where they are ranked from top to bottom? So researchers use a test to determine if the critical value obtained by comparing ranks and their association. So for this case, we can assume a miracle occurs. You don't need to worry about what happens behind this statistical test. You end up with something like this. So here's early training. Yes and no. There's 4 who's, in this case, 1 is yes, 2 is no. So there's 4 who said yes, 2 that said no. We want to know if that's anything to do with the rank. They rank them based upon where they are. So the average ranking for those who said yes was about the 6th place, and for those who said no was about the 4th place. And we want to know, are these statistically different? So we go down here. Because we have exact significance, we can say that this is not less than 0.05. So there is no difference. It makes no difference to that. And we use a one-tail here for a couple of reasons. One, because actually our hypothesis was a directional hypothesis. But two, also, if you have exact significance, you really need to use that because it's such a more precise test. So, can we reject the null in this? No, we can't, because we don't have any evidence to suggest that early training has anything to do with ranking. I'll give you another example. Let's suppose we're interested in determining whether age at diagnosis of type 2 diabetes is different for male and for females. So we have males and females, and we have the age at which they were diagnosed. Well, this doesn't really help us with anything. So what we want to do is convert this into numbers. So we have females and males, and we have the age. And you can see by doing that and starting to rank them by age and by also attaching their gender, we can start to come up with rank intervals. Remember, we want to know if age and gender had anything to do with diabetes. So this is a two-tailed test. We didn't make a determination ahead of time. And this is kind of like an independent samples test. That's why we're using this Mann-Whitney. So it gives you this information down here, and this seems like an awful lot, but remember what we're looking for, if we can get it, is exact significance, two-tailed. So this is not less than 0.05, and that would tell us that the gender doesn't have anything to do with when they're diagnosed with type 2 diabetes. Give you another example from this one about non-fatal overdose. Let me make this a little smaller. Scroll down through here. We can see in the results what they're doing is they're comparing heroin use, and this has to do with using methadone for heroin treatment. How long they're using heroin, the severity of dependence scale, and that's why we're using Mann-Whitney on this, is because they've got a scale, and because this is rank order data, that's what's going to lead us to using the Mann-Whitney. If you keep coming down through here, methadone maintenance treatment says that subjects in methadone maintenance treatment, it comprised 25% of the sample, so you have 75% who are not in that treatment. These subjects, those, the MMT, were more dependent on heroin in comparison to the remainder of the sample. And you get this U score right here, sorry about that, and a P less than 0.05. That means that was a significant difference. And further on it says, despite this greater dependency, MMT subjects had used fewer main drug types in the previous 6 months. That's a significant difference, and had fewer days of heroin use. Here's an important note. It says, although this difference narrowly missed out on statistical significance, 40 days for MMT subjects versus 57 days for others. That's not the same thing. You cannot associate that with significance. Either, as I said before, either it's significant or it's not. You can't have it both ways. So they really, I think, misrepresented themselves in this by saying that it narrowly missed significance. No, it's either it is or it isn't. So that's an example of a Mann-Whitney U. If it doesn't ever really say this U, always this capital U that's in italics, always means Mann-Whitney. Now, remember a few things. One, if ranks are not already applied, then the researchers are taking interval or ratio data and converting it into ranks. For example, with the age and the gender for diabetes, we took those ages and we could put them into ranks from youngest to oldest. The other place this is useful is for Likert scales. If you've ever filled out a survey on how do you feel about ice cream on a scale of 1 to 4, then I ask you how do you feel about pizza on a scale of 1 to 4. Those are Likert scales. That is Likert scale. That is ordinal data or rank data. And really you're supposed to be using Mann-Whitney. You cannot take the mean on a scale of 1 through 4 because the difference or the distance between 1 and 2 on that scale is not the same as the distance between 2 and 3, which is not the same as the distance between 3 and 4. What causes you to go from a 3 to a 4 is different than what causes you to go from a 2 to a 3. And what causes you to make that decision is not the same for everybody else. Because those are not all the same scale, they're not interval data, and you cannot take the mean of it. If you can't take the mean of it, then you cannot do any of the parametric tests. I have this about PDAS that is for people that spend a lot of time teaching, so I'm not going to get into that. So, although you will see people do this a lot, you're really not supposed to be doing it. And there are a lot of people from psychology and lots of other areas who'd argue that, yeah, it's okay, because how can you say that interval is any different than ordinal? I still just believe that there are certain tests for certain types of data, and you need to stick with them. The next thing we're going to look at is making the problem worse. And I'm going to pause here and start a new video.